All right, welcome back for the second talk of the morning. And switching gears a little bit, we're going to look at quantum chemistry from the perspective of computational complexity. We've got Jiaqing from the Simons Institute, how Hamiltonian complexity differs from quantum chemistry, and do complexity results prove or disprove quantum advantage?
Okay, thanks for the introduction. So yeah, this title is long, so Sandy spent a lot of time reading this title. In last talk, Martin gives an introduction to like computational chemistry and talking about, what's the potential quantum advantage. So in this talk, the key focus is again quantum advantage. So we try to discuss quantum advantage, but from a more quantum info perspective. So more precisely, I'm going to talk about some complexity results related to quantum advantage. But the key focus would be like how does those results differs from like the models, assumptions, or interpretations in quantum chemistry. Or in other words, I'm going to talk about some complexity results. And the guiding question in your mind should be, does these results really prove or disprove quantum advantage? So okay, this is the title. So to begin with, I want to give a short introduction of background and specify the question we study. So I see that I'm going to talk about some Hamiltonian complexity and quantum chemistry. Both of them are very big fields. So in this talk, we will only focus on a specific problem, which is related to quantum many-body system and ground energy. So from very intuitive level, like what we want to do, as Martin already explained, is just try to estimate some property of molecules and materials. Or slightly more formally, just like the problem is similar to something like you give molecules or meta cluster or some materials. You want to estimate some quantity called ground energy. So intuitively, this is the lowest possible energy that a system can have. But I mean, just some kinds of property of the molecules. And I will give a more precise mass definition in the following slides. But before that, let me just briefly mention like the reason why we care about this quantity. In fact, ground energy plays a fundamental role in like chemistry or material science. So as in the previous talk, if you can compare ground energy, you can use this to determine like whether this molecule is stable or not, or whether certain reaction will happen or not. In material science, if you can compute ground energy, like you can use this to predict or understand phase diagram, like when a material will be a conductor or superconductor. At least for towing model, you can do something like this. So this is a short introduction. So okay, so since I'm going to talk about complexity, we need some more specific mass model. So as I said before, like the key question in this talk is called ground energy estimation, which is, just to estimate the energy of a given like NQB system. So let's begin with the definition of NQB's local Hamiltonian, which is a big matrix to describe the energy of a certain system. From mass level, like NQB's local Hamiltonian is just a big matrix which can be written as a sum of some local terms, where each local term only acts on constant qubits. And the key concept is just ground state, which is just the minimum eigenstate of this big matrix. And the ground energy, which I highlight as lambda h, is just the minimum eigenvalue. So in summary, what I'm saying is the problem we try to study has a very simple like formalization. Just you try to, the ground energy estimation problem is just to estimate the minimum eigenvalue of a big matrix. So this is the main question we care about. Any question? Okay, so it seems most people are familiar with these concepts. But in case you are not from quantum info, like I give an explicit example of local Hamiltonians. So for example, in the Heisenberg model, this big matrix is defined on a graph where like the term is summation over all the HKL, where on each edge there are some like x, x, y, y, z, z term, which x, y, z are just certain like 2x2 matrix. So this is just an example. Okay. So since I claim I'm going to talk about something about quantum chemistry, So it will be good for me to also introduce a similar notion to local Hamiltonian, but slightly different. So this is N-mode local fermionic Hamiltonian. So this is more natural used in chemistry. So those kinds of Hamiltonian are mainly for local. So here I only introduce the for local version. So similar to local Hamiltonian, like fermionic Hamiltonian is also a exponential size matrix, which can be written as the sum of some simple terms. So here the terms is of form gamma, ijk, or ai, aj, ak dagger, al dagger. So you may ask, okay, what's those notation? So for the gamma, it's just a complex number. So it's just a coefficient of some terms. And the ai, aj is called the fermionic annihilation operator, but I intentionally don't write down the name because I think it's not that important. So if you just want to get an intuitive understanding, you can just view this AI. I mean, in fact, this AI can be written as like the product of simple matrix, which AI can be written as Z1 tensor Z2 tensor Zm minus 1. And for the ith qubit, its operator maps 1 to 0. In case you don't know which is matrix, so like this AI and 0, 1 are just some certain like 2x2 matrix. Any question? Okay, so
why do you have a for local Hamiltonian? If I remember correctly, Martin had a two local.
Two local correspond to free fermions is classically easy.
You mean like
so,
order 4 in the operators?
So like if you consider like like Schrodinger equation, there are some terms correspond to like potential. So like the potential of the electron. Some terms according to 2x2 interactions, those kinds of terms. So one of it will correspond to two local terms, and one of them will correspond to four local terms. So I'm saying like.
I'm just wondering if all the ij can be different.
Yeah. But that's okay. Yeah, right. So this is a very general form. Yeah, but in the following, I will talk about the more specific form used in. Yeah, thanks for the clarification.
Hey, Jiaqing, I have a question. So when do we use second quantization? When do we use first quantization? It seems like the previous talk is more about the first quantized version.
I would say I'm not. I don't know. I'm okay. So give a background. It's like I'm mainly from like computer science background. So like this is more like a summary of my interaction with chemists. Yeah. Interesting. Okay.
Yeah, so are you saying that if you have additional quadratic terms, then like that is a special case of this? Because I don't see that. Like if you have like in quantum chemistry, like you have also quadratic terms, right?
Yeah.
So like second order. So are you saying that this somehow is subsumed, or or is this just a special case of like local?
For me, you mean like this for local or what?
Yeah, I mean for local would also have terms like gamma, ij, ai, aj dagger, right?
Oh yeah. Okay. Oh, sorry. Yeah, right. So here IJK can be arbitrary. They can be the same or be different. I mean, this is just a general operator. Like
say that if I want to have quadratic second order terms, then I can reproduce that by choosing gamma appropriate.
Or probably you are right. Like I mean, so let me correct my definition. The most natural definition would be. Some false term. Is this good? Okay. Yeah. Okay. Maybe yeah, you're right. So, yeah, but I mean, this is just a definition, and the only thing I want to briefly mention is. Like this is this matrix compared to like local Hamiltonian will be highly non-local, because each AI acts on like ith qubits. So like so intuitively, like I'm just saying like local fermionic Hamiltonian is intuitively much harder than local Hamiltonian, but just from an intuitive way. Okay, so this is just a definition. So now I'm going to give an outline of what I'm going to talk in this talk. So as I said before, like my main focus will still be in like the complexity part, which is my field. So so in this talk, I was talking about like complexity of ground energy estimation, but from a quantum advantage perspective. So I mean, just imagine you're thinking about, okay, we try to get quantum advantage from ground energy estimation. So the first question you should ask yourself is like, I mean, do we even expect quantum computer can solve this problem? So I will begin with the worst case hardness for ground energy estimation, which is some kind of QMA complete result, which I will mention in details later. And then I will talk about, okay, when if this problem is worst case hard, when will it become like quantum easy, and when this problem will become classically easy. And a disclaimer or like a remark is like in this talk, although I will focus on complexity results, but the key, the intention is not listing complexity results. Instead, I'm trying to explain like, to explain what I learned from like chemists, to explain how does those results differ from model quantum chemistry in terms of model assumptions and interpretations. So, okay. So let's first begin with the first part is, so before we're thinking about quantum advantage, you should, first ask yourself a question, like what's the worst case hardness? So the summary of this section is ground energy estimation is quantum hard in the worst case, but there's no hardness result for natural Hamiltonians. So
ground energy, are we strictly talking fermionic in this talk from now on, or do you just mean in general ground state energy estimation, just so I know how to interpret your statement?
So I mean in general, yeah. And you will see the details. I will talk about both local Hamiltonian and fermionic Hamiltonian. So so first, like the worst hardness is like ground energy estimation is quantum hard in the worst case, which basically means quantum computer cannot solve this problem. So if you ask like more precise statement is local Hamiltonian problem is QMA complete. So here local Hamiltonian problem is a decision version of ground energy estimation, where you are given a NQB local Hamiltonian H, and instead of computing ground energy exactly, you choose to decide whether this energy is greater than something or smaller than something, and the precision is said to be like is typically said to be like 1 Raponi. And the QMA, if you want to know some details, is just a quantum analog of MP. There are some precise definitions, but if you only want to, remember some very intuitive sentence, this complexity result just says the title is like ground energy estimation is quantum hard in the worst case. So from this perspective, it seems like everything is bad, and you might think, okay, probably like if I consider like more specific Hamiltonian, like it might be easier. But unfortunately, if you're looking up in the literature, especially for the local Hamiltonian case, you will realize, even if you restrict the Hamiltonian on like geometry local, for example, 2D or 1D lattice, it's still QMA hard. And this kind of hardness even holds for like very, very special system, like 1D translation invariant system. So for translation invariant, so as I draw here, like every term are just the same. And the only difference is like they work on different QDs. And one thing I want to mention is like in this result, the dimension, they work on high dimension QDs rather than qubit. Any question?
Yeah, what precision do you need to estimate the energy?
1 Raponi. So this is some known complexity results, and if you think about this problem and try to look up, say when this problem can be easy, you will really feel desperate. It seems like there's no hope to do that. So you ask yourself, the question is like, do we believe quantum computer can solve this problem? Like, why do we believe this? So the answer is also easy. It's also in one sentence, just say, okay, because the problem in practice is not that hard. So but I personally find this sentence is a bit vague, and I'm going to give you an explicit example when we don't have any QMA hardness results. So the model I'm going to introduce is called Fermi-Haber model, which is which you can prove some kinds of QMA complete result, but I would say there's no hardness result for the model studying chemistry. So let me begin with introducing this model. So Fermi-Haber model is defined on a graph. For example, you can define it on a lattice. So on each side, there are two fermions of different spin. As Dominic mentioned before, a more natural form of Fermionic Hamiltonian of this form is like you have a term. So okay, I'm just saying like the Fermionic the Haber model is a summation. They have two terms. One term is defined on the graph, which basically describes like the electrons hopping from one side to another. So this is the nearest neighbor interaction, and the quadratic term like acts on each side, which describe like how two electrons, if they stay in the same side, they will have some repulsion to each other. So here I again use the fermionic operators, but if you don't like it, you can just imagine we use them as some certain like product or simple matrix. Any question? Yeah.
What exactly do you mean by no hardness result in chemistry? Like, what would a hardness result in chemistry be?
I will say it later, in the next slide. So this is just a definition of like Fermi-Haber model. I just want to briefly mention why this model is important is because this is used to model like the solid materials and the models of, it's the Toy model to understand the transition between like conductors or superconductors. For simplicity here, I intentionally ignore some tricky part. It's like, so in chemistry, when they really do this model, when they say they compute ground energy, they need fixed particle number. So basically, this means like they compute the minimum energy in a certain Engel space. And also they not only consider nearest neighbor hopping, they also consider like slightly far away hopping. So, but this model is the simplest model. So this is just Fermi-Haber model. Like I'm going to explain, okay, what do I mean for QMA hardness result, and what do I mean for there's no hardness result in chemistry. So given this Fermi-Haber model, like there are two inputs. There are several inputs. One is the T, one is the UI, and also the graph. So in fact, you can prove this model is QMA complete if you allow yourself to do something a bit like abnormal. So for example, you can prove this model is QMA complete if it's on a generic graph, or you can prove it's QMA complete if it's on 2D lattice, but you allow the coefficients to be different. So this is some results you can prove. But as I mentioned before, I'm claiming like there's no hard result for like the Fermi-Haber model in chemistry or in condensed matter physics. It's because the model they study, if you talk with them, you will realize this model is, it's on 2D lattice and also translation invariant. So for translation invariant, I'm saying like this T. So like for the hopping terms, so different sides, all the sides have the same uniform like coefficients, and also for this like on-site interactions. So the intuitive reason is also simple. It's like if you model a materials, like ultimately you need to consider an infinite system, and you don't view like different like you don't view like electrons in different sites behaving in a different way. Sorry.
Yes, I have a question and a comment. I guess the question is. Sorry, thank you. Question and comment is the question is okay, let's assume you can modify the weights, right? Getting unit weights we don't know how to do this for QMA hardness. That's my comment, right? In general, but for for like the Heisenberg model and things like this. But presumably you can get translation invariance if I allow the weights to be different. Like what stops me from applying like Sandy's like let's say previous techniques and so forth?
Because Sandy's techniques works for high dimensional QD. I think
right.
It does. So here is Fermi's. Like if you translate it to like qubits, to like qubit Hamiltonian is always QB. Probably Sandy have a better explanation.
I mean, you can take some.
Are you asking about putting coefficients on the individual terms, different ones?
And you just get translation invariant. You just by encoding your qubit construction to like a Fermi qubit to Fermi construction.
And you're tuning the coefficients on each edge. I guess it depends on your definition of translational invariance then. That, we had defined it to be exactly the same term with no coefficient on the edges. If you can tune your coefficients, yes.
And then it's not translationally invariant.
Then, yeah.
Sorry, no, maybe.
We can always block few sides together, and there is one side.
You mean to encode the hardness?
Oh,
I mean, you can
mean
try.
to get a qubit from a bunch of qubits.
Why not?
Yeah, maybe like that's an open problem. If you can prove that, that's surprising.
Yeah, but there are different levels of translational invariance. I mean, you can ask that the terms exactly be the same, or you can have a set of fixed terms and tune the coefficients. If you can tune the coefficients like she's had on the previous slide, then you do get hardness. So.
What's the question?
Okay, I think I was also confusing the fact like I think typically we need like perturbation theory to get like these nice models coming out, right? And we don't know how that plays with I think the translation invariant constructions at all, as far as I'm aware. Okay.
Very well question.
Oh yeah, so I'm a little confused. I can see how this models like some many-body physics situation, but I don't see how a translation invariant Hamiltonian models the electronic structure problem we saw in the last talk. Like Martin's posed like the central problem in quantum chemistry is electronic structure for a particular like finite number of electrons, right?
So first, like finite number electrons. So Fermi's does not mean the number of electrons. Fermi means how you discretize the Schrodinger equation. So it's an orbital. Yeah, so like the number of Fermis does not correspond to the number of electrons. And also like this model is a more simplified model for compared to general like electron structure. Because I mean, as you see, this is on 2D rather than 3D. Yeah.
Still expect it to be translation invariant. Like do the models corresponding to electronic structure with translation invariant?
So for general like electron structure, Hamiltonian, like Sandy also have a Kuhlmann-Hardness paper, but for that paper you need to choose orbital in a strange way. So for example, the most standard, one of the most standard orbital is just the wave function of like hydrogen. But if you allow like strange way of choosing orbital, how you discretize the 3D space, you can get Kuhlmann-Hardness result. So that's no hard result for a different reason. Any more questions? Okay, so this is all I want to say in section. So like as far as I know, there's no Kuhlmann-Hardness result. If some of the audience think you can prove Kuhlmann-Hardness, that's even surprising, and then that's one of my goal of this talk. And also one thing I want to mention like is this is really a model which is actively studied in like computational quantum chemistry. And it seems classically hard for classical heuristics from some survey I read and from my discussion with Garnet and his students. So basically, I'm just saying this is an interesting model where like it's an explicit model, no Kuhlmann-Hardness results, and it seems classically hard. What's the question?
Okay, so this model cannot be computationally anything because it's just a two-parameter like function, right?
Yeah, that's a great question.
The lookup table would solve this.
So it's similar, and I mean, Sandy predicts this question. So it's similar to the reason to how you can prove like translation invariant system. So the only input is a number n, but you can still prove QMA-XP hardness. Yeah. So like it's not impossible for you to prove hardness results for such translation invariant model.
So like, does the lookup table fail because like you are looking at a very big n, or like why doesn't the lookup table suffice?
You mean lookup table for what? For T and mu?
Yeah.
But you cannot solve this Hamiltonian, right? And also I think slightly slower than my expectation. Probably I can take some of those questions offline. Yeah, so in summary, like in section 1, I'm just trying to introduce one specific problem to convince you this problem is not QMA hard in the worst case. But it's not QMA hard like for the practical case. And I mean, if you have more thoughts on how to prove the hardness of this problem, like we can chat offline. So I suppose this to be a warm start while it takes some time. So in fact, my main focus is on the second part, is when can we solve can we solve like ground energy estimation. So a short summary is I will show that I will talk about under certain assumption, this problem ground energy estimation will become quantum easy. However, I came through some questions for the assumption, so we are still unsure. So what do I mean? So as I said before, like ground energy estimation is QMA hard in the worst case. I mean, to design algorithm, you need to make assumptions. So one of the most popular assumptions is called guided states, which is a state which has 1/Pauli overlap with the ground state. So it's something which is non-trivial close to ground state. And besides, we assume it's efficient to prepare on quantum computer, such that you can use this state as a warm start of your algorithm. So in fact, if you have guided states in hand, like it's not that hard to, get the ground energy. You just use this phase estimation, which is a quantum algorithm can extract ground energy from ground states. So basically, it says like if you have a good guided states, then like after apply phase estimation, like with non-negligible fraction, like probability you will get the ground energy. Although it's simple, but in fact it's one of the most popular quantum algorithms. I think probably 90% of the quantum algorithm like are based on this method, and most of this work are just trying to to further improve the efficiency of this algorithm, is to reduce the size and the depth cost. So the key thing I'm going to talk about is not to reduce the practical cost. Instead, I'm trying to justify like whether this kind of algorithm has quantum advantage. So the basic question is something like this. So it's with guided states. As you may already say, guided states is a magic that make ground energy estimation to be quantum easy. But you should also, before you claim quantum advantage, you should also ask yourself, does this problem, does this warm start also makes the problem classically easy? So this problem is serious, especially because you may ask yourself, where do I get guided states? So guided states is not magic, and we suppose we get guided states from existing classical algorithms, which means we naturally have like classical access to those states. So you may ask, okay, if classical algorithm can utilize these states, can they use to solve the ground energy estimation problem? So in the following, I will mainly focus on talking about three things. First, I will talk about the complexity result, which says, okay, there is quantum advantage. And then I will talk about Kim's question, on some why they are not satisfied with this result, and some further results on possible dequantization. Since we are going to talk about complexity results, so to be slightly more formally, so let me recall what is ground energy estimation with guided states. So the input of this problem is a local Hamiltonian edge, and a vector and some classical access to a big vector mu. So here mu represents the guided states, and the classical access you can just imagine is a polynomial circuit, which can compute the amplitude and they can do some sample access. It's like they can sample each entry of mu according to the two law. And besides, there is a precision parameter which controls the output. And the problem is that mu implicitly represents guided states, and the goal is to estimate the ground energy with certain precision. So here, I want to emphasize that in this work, the precision is a multiplicative approximation is like m times epsilon, where m is a number of the terms. But here, epsilon can be arbitrary, can be a constant, and it can be 1/Pauli. So this is a setting. So okay, if you only want to remember one sentence, what I want to say is, previous work has elegant explanation of what is quantum advantage. So they say quantum advantage is achieving higher precision. So what do I mean? So suppose we want to estimate the ground energy to epsilon precision. So this work proves that if the epsilon is 1 over pony, then this problem is BQP complete. And if epsilon is constant, then this problem is in BPP. So in other words, it just say like if we believe BQP is not equal to BPP, then quantum computer can estimate ground energy to a very high precision, while classical computer cannot. So this is the proposed quantum advantage. Any question here? Okay, so
What is the scale of epsilon that chemists actually care about? Is it constant or is it 1 over m?
so in fact, I think this problem, so like the answer to your question, I think depends on which system you're talking about. So I think, yeah, you can correct me if I'm wrong. So I think for like a fixed size system, for example, you consider certain molecules, I think they want to, estimate, so the total error should be a constant. So the error will, the actual error in terms of Hamiltonian will be 1 over n. But if you consider infinite system, I think, so it's some, for example, like Haber model, I think they want estimate to a constant. Because like you want to compute some value which makes sense when you increase the number particles to infinite.
So the version of the problem where you just want to get it to constant, like to constant in actual units, like 1 millihartree or something, that problem is unsolved. Like we don't know if it's in BPP or BQP.
Yeah, and also, if you talk about the practical thing, like this BPP is exponential in precision. That's not good. It's exp 1 over epsilon. Yeah, like even like this, even you're only looking for constant precision, this is not that good algorithm in practice.
Sure, but just to comment on Robin's point, Robin has a point here, right? Like the result we showed here was for worse than 1 over n, right? I understood Martin said earlier is like the error you want is typically 1 over n in a chemical system.
Yeah.
And that hardness result, the 1 over poly, is like sub 1 over n.
Yeah. That's also another gap between what you can prove and yeah.
So I mean, like for example, 1 over root n or something is what you mean, or you mean it's like. Do you mean that, or do you mean 1 over n squared? I'm just asking which direction. What do you mean?
1 over n cubed or something like that.
Yeah. Because it's like 1 over n cubed, maybe 1 over n squared is the best you can get. Because it's based on these like circuit Hamiltonian constructions, and there were typically there's a roadblock 1 over n squared.
I see. Okay, thanks.
We don't know how to get it down to 1 over n.
Yeah. So this is elegant complexity results. But as you may already notice, I at least have 20 more minutes. Basically means like this is not end of story. So what's the next story? So whether we believe like the previous complexity results already capture the hardness of classical algorithm depends on whether we model the guided states in the right way. So in fact, some chemists and physicists they ask the same question, and so there is a paper which titled as evaluating the evidence for exponential quantum advantage in ground energy estimation. And more precisely, what they are doing is just they numerically check the overlap between guided states and ground states. So if you look at the paper, there have some table, and but I'm not going to talk about the details of this table, but instead I'm going to summarize what they are claiming. So I think basically they're claiming two things. First is for hard Hamiltonians, for example, surrounding interactive system. It seems like classical algorithm cannot find good guided states. It's the overlap between guided state and ground state will decay exponentially fast in terms of number of n. And on the other hand, like they found that if the classical algorithm are good enough to find some non-trivial thing, and then the final state of the output will be something much better than your standard definition. So in fact, they somehow believe like for those systems it's classically easy. But from a theory side, like we can ask the question is like, so from a theory side, like what they are saying is like, your previous PQP results, might make a wrong assumption, just in terms of the model of the guided states. And the key question in the following talk is just to understand, okay, if the guided state is much stronger, like can a classical algorithm like refine this energy to ground energy? So that's a question in the following talk. So before I go to details, I need to give a definition of what is strong guided states. So recall that guided states is a state which has 1/Pauli overlap with ground state. And for strong guided states, there's no standard definition. But I would say, due to some technical reason, you can define it as entropy-wise 1/Pauli overlap with ground state. So it's, for example, it's like this formula is like, you may consider eta is a guided state, and phi is a normalized ground state. And the entropy-wise overlap is just like for each entry, the inner product is greater than the norm divided upon n number. So this is strictly stronger than the standard guided state definition, but it's still non-possible. Like it's still like non-trivial to dequantize. So I'm not claiming this is the best definition for strong guided state, but this is just the first step you can try. And I say like the following talk is just try to focus on like with strong guided states, can ground energy estimation can be classically easy.
Is strong guided state stronger notion than guided state?
Yeah, if you sum over x, you will get a Hamiltonian.
What's x?
Sorry, this computation basis. Yeah. This is if you sum over computation x, this is the left part is the inner product of eta and phi, and the right part you get the number. So yeah, so you might have a lot of questions on like whether this definition is reasonable or not. But like sorry, like so here I'm just give a possible definition of guided state or strong guided states.
Yeah, but what's phi and what's eta?
So eta is a normalized strong guided state, and phi is a normalized ground state. So this formula just defines the property that eta should have. So it's an entropy-wise overlap. Yeah. Okay, question?
So why do we think we can find a strong guided state?
So as I say, like instead of saying like this is the best definition, this is just the first thing you can try, and I will explain why I think this is a good definition in the next slides. So maybe I should first talking about the next slide. So yeah, so like so in the following, I'm going to give you some like some kinds of like specific results to demonstrate what I'm saying. But before that, I want to give you a summary of what I'm trying to say. So from high level, I'm trying to say like, or trying to discuss whether it's possible to design classical algorithm for ground energy with strong guided states. And the thing I really want to convince you is I want to convince you we need a refined understanding of why ground energy estimation is classically hard. So what do I mean? So if you ask yourself, I mean, since we are considered quantum advantage, just ask yourself like why you believe ground energy estimation is classically hard. If you ask a random person or if you ask yourself, the first answer you might be is okay, it's because this problem is exponential size. But I want to convince you this is not the case. Like exponential size is not necessarily mean this problem is classically hard. So an intuitive example is, I mean, in the SAT problem is a special case of local Hamiltonian, where the solution space is also exponential size. But in practice, randomized algorithm just works really well. Just randomized algorithm is able to explore exponential size. But of course, this is a very vague statement. I'm going to give you a more precise or more like, yeah, rigorous results, which says like randomized algorithm can almost estimate ground energy with strong guided states if the Hamiltonian is sign-free. So the first result, I'm just trying to, convince you like this is not, exponential size is not really the reason. Then like if you think about this problem like much harder and say, okay, why this problem is classically hard? You might come up with a concept which called sign problem. So sign problem is again something complicated. Based on different algorithms, people define sign problem in a different way. So roughly speaking, you might interpret it as a difference between why probability theory cannot simulate quantum mechanics. So you might think, okay, that's the reason why randomized algorithm cannot tackle an inherently quantum problem. But however, like I want to convince you, or like try to convince you that evidence that some problem is not necessarily, even some problem is not necessarily obstacle for classical computer, especially when you have a guided state. So I think in practice, people call those states reference states. Although it's unsure like whether those reference states are really captured by my definition of strong guided state. But at least for those kind of states, you can say why it is possible for guided states to help resolve the SAM problem. So this is a summary of what I'm going to say. Any question on this summary?
So is the idea in J25, I guess, to use the assumption to run like Ravi's algorithm for like stochastic?
No, like so it's another different one.
Ah, cool.
So stochastic, so there's okay, I will explain more details.
Okay.
Yeah. So okay, you have a question?
Yeah. So what does almost works mean?
You are saying the following. So okay, so yeah, so the key information I want to tell you is classical algorithms are more powerful than you might think. And all the following talk are just techniques. So okay, let me talk about more techniques like to resolve your concerns. So the first thing I'm going to talk about, as I promised, is like I'm going to talk about for SAM-free Hamiltonian. With strong guided state, you can almost like estimate ground energy. So first, like let me explain what is SAM-free Hamiltonian. So for SAM-free Hamiltonian, we call it stochastic, which is a Hamiltonian such that all the off-diagonal entry is smaller than 0. So like the technical reason why this problem is more close to classical problem is complicated, but an intuitive reason is very simple. It's just like for such matrix, you can transform this matrix to a non-negative matrix, where you can naturally connect to a Markov chain. So that's the intuitive reason why SAM-free Hamiltonian is more close to classical probability theory. And this is also like, from this equation, you can also say for general Hamiltonian, this is not true. So that's why you need to resolve SAM problem. So what do I mean when I say it's almost solved, ground energy estimation? So roughly speaking, like for SAM-free Hamiltonian, if you have strong guided states and you have some slightly more classical guiding information, which I will explain later in the next slides, then you can efficiently estimate ground energy for the decision version. So this is based on projection monocolour method, which is something like a random work on computational basis, and the transition probability is proportional to the amplitude of strong guided states. And the only thing you need for the guided states is the classical query access. Is whenever you try to jump from X to Y, you query the amplitude, and this somehow tells you what's the transition probability you need to set. And when I say almost, you need something slightly more than strong guided states. So you need a warm start of this Markov chain. And you also need some other classical guiding information, which you can check in the paper. What's the question?
Does the guided state also need to be stochastic, like SAM problem?
Oh, yeah, in this case, yes. Yeah. But in general case, we don't need that. So this is...
Don't you get that from the definition of strong guided? Because you're at least like 1 over Pauli overlap or something like this with state which will be non-negative by definition?
Yeah, so like, so we'll say like there exists one, if the ground state you choose is the sign, is the one which of all positive sign, yeah.
Okay.
Yeah, so like, yeah. So to make this nice simple, I somehow intentionally ignore some like details, so it's not precisely correct everywhere. But roughly speaking, like for SAM-free Hamiltonian, I'm just saying like randomized algorithm is powerful. So here, like I mentioned, like the input is not only strong guided states. You also need some warm start of the Markov chain, which is an n-bit string, and some other classical guiding information. So if you want to get a more clean results, as the paper does, in fact, you can consider a weaker problem, where you view strong guided states as witness instead of input. So then we come to our favorite Hamiltonian problem, where like we are given H, and we try to decide whether the energy is low or high. And in the yes case, you promise that there exists a strong guided state. So if follow this formulation, then our key conjecture is just to prove then our key conjecture is just to prove like local Hamiltonian problem with strong guided states in MA. And the Bravi's paper, which is the sign-free one, just prove like this conjecture is true for sign-free Hamiltonian. So like back to our story. Our story, we try to discussing whether it's possible to design classical algorithm for ground energy estimation with strong guided states. And we say, okay, this is okay for sign-free Hamiltonian. And then like the question you may ask is like, okay, why do you believe this can be generalized to, or in some sense can be generalized to general Hamiltonian? Like, how do you circumvent sign problem? And as I said before, like the way you use sign-free Hamiltonian is because you can translate it to a non-negative matrix. This is generally not true for general Hamiltonian. But even so, like, there are evidence to show that strong guided state might help the resolve the sign problem. So for evidence, I'm saying like I'm going to talk about the necessary condition, necessary like results, rather than directly solve the problem. So so again, like we consider for simplicity, we consider the weaker formalization, where we review everything as a weightless. So the problem we consider is local Hamiltonian with succinct ground state, which can be viewed as extreme strong guided state. So what do I mean? So we are again given a local Hamiltonian H, and we try to estimate the ground energy, decide whether it's lower than something or greater than something. Where in the yes case, we assume there is a succinct ground state. So succinct ground state is a ground state where succinct means you have certain classical access. So here it means you have a polysize classical circuit to compute the amplitude. So like from a TCS view, you can just interpret this as a classical query access where you allow an unknown normalization factor. So you don't allow this state to be normalized. The intuitive reason is because in the previous algorithm, the randomized algorithm, as you can see, we only care about the ratio instead of the like actual like number. And as I promised, I claim like this is can be modeled as an extremely strong guided state, just because it's something even better than strong guided state. And the main result we prove is like this problem is in fact MA complete. So this is the results. And before any techniques, the key question you should ask is, how does this result relate to previous results? Or relate to our conjecture? So these results prove like local Hamiltonian problem with succinct ground state is MA complete. And the conjecture is we try to prove, you can dequantize with respect to strong guided states. So this conjecture is a necessary. So like the succinct result is a necessary condition for this conjecture. It's like if one day you can really prove this conjecture is true, you will be able to reprove this succinct ground state result. And from a technical side, like this result, in fact, demonstrates a way to resolve the sign problem because, as I said before, it's non-trivial to connect a general Hamiltonian to Markov chain. And even for like the local Hamiltonian problem with succinct ground state, previous MA result is only known for sign-free Hamiltonian. So like I also have one slide for explaining what's the techniques. Very roughly speaking, so as I said before, like the key thing I want to convince you is like with guided states or with certain guided states, it's not impossible to dequantize. So in fact, if you're looking at the old literature, like in chemistry or physics, they already have numerous methods to, handle the sign problem. So here, the one I use is a fixed node quantum Monte Carlo method. Roughly speaking, is a method to transform general Hamiltonian to stochastic Hamiltonian. So slightly more details is like given a general Hamiltonian H, and given a reference state eta, this method this method write another Hamiltonian f, such that this here f is stochastic. And the relationship between f and h is like the ground energy of f is always a lower upper bound of h. So it always, if you can compute the ground energy of f, it always give a meaningful answer. And this, and if eta is a true ground state, then the ground energy of f equals ground energy of h. And if eta is not the true ground state, I think in practice they use this in a more heuristic way. But the main problem of this method is, in fact, the log of f is exponentially large. So it's very non-trivial to simulate this Markov chain, even if it's stochastic. But even so, there are some variants of this method, which is based on continuous Markov chain. And this is exactly what we are using in our paper. So basically, I'm saying to prove, to resolve the sign problem, there are some existing literature, some existing randomized algorithm which is abnormal. So the final algorithm we use is a Markov chain, but with varying step size. And I don't know any more normal randomized algorithm can tackle this problem. So this is a summary of section 2. So in summary, I'm trying to explain what's potential quantum advantage with respect to guided states. And the first result I said is if we are given standard guided states, then quantum advantage is achieving higher precision. But the chemists but this is not the end of the story, because chemists raise question on the definition of guided states, which might potentially invalidate the quantum advantage from the BQP results. And after that, I talk about some evidence about possible classical algorithm with strong guided states. And the thing I want to say is guided states might be a way to might be able to help you to resolve the sign problem. So this is a summary of section 2. Any question here? Okay, so finally, let's come to the classical part. So for this part, most algorithms are heuristic, so I only have one slide about something I want to share. So in summary, I want to say even if some results, for some problem, ground energy estimation is inside BPP, this does not necessarily mean there's no room for quantum advantage. So what do I mean? So as I said, I'm come from computer science. I'm not expert in computational chemistry. Probably you can ask Martin. But here I put a perspective article by Garnet about quantum chemistry, open problems, classical heuristic, and quantum advantage. And there is a particular thing I want to share from this perspective article is how chemists thinking about the cost of the classical algorithm. I think this is something I really want to share. So, and this is the final page of this slide. So roughly speaking, they believe empirical observation suggests that for many systems, the classical quantum chemistry method satisfies the following cost conjecture. So basically, it says the most classical algorithm, the cost is consists of two parts. One is the state preparation part, which is find an appropriate reference state. So even for classical algorithm, they need some kind of guided state, although it's not of our sense. So according to my understanding, something in the same phase or something has the same symmetry. And if they can, so after finding this reference state, then they do some refinement. So so they believe this refinement part for most systems is Pauli in N and Pauli in 1 over epsilon. So this is part of the belief that he believed classical algorithms are efficient. But as I said before, if you read this perspective article, you will realize that even for chemists, even they think the algorithms are polynomial, this doesn't mean there's no potential quantum advantage. So according to this article, he thinks the most potential quantum advantage is to improve the dependence on this precision, so improve Pauli 1 over epsilon. so for most systems, they believe this dependence on like epsilon is pony, but it's still possible for some system. This refinement grows exponentially in 1 over epsilon, and there are rooms for exponential quantum advantage. And the final comments I want to give is like, I mean, so in these two lines, I'm talking about like potential quantum advantage to improve this refinement part. You might also ask whether we can speed up the state preparation part. So I feel this part is a bit tricky because so even in the classical algorithm, this part is more like a NP search problem. So it seems hard to imagine how could you get exponential quantum speed up for NP search problem. So this is the table, but it's exactly what I'm saying. So finally, just want to give a summary. So a summary is like, I mean, as I say, like I talk about some Hamiltonian complexity results, and I'm trying to explain, according to my knowledge, like how those results differ from quantum chemistry. So the first thing I'm saying is like ground energy estimation is quantumly hard in worst case, but no hardness results for natural Hamiltonian. For example, like the Fermi-Haber model studied in chemistry or condensed matter physics. And the second thing I'm saying, like so like for the quantum algorithm based on guided states, so for practical guided states where you get from real like classical algorithms, the ground energy estimation is quantumly easy, but somehow still unclear whether it's also classically easy. And finally, I talk about some perspective article, and the only message I want to give is like, even like for some problem or for most problems inside BPP, this does not necessarily means like this is classically easy, and means there's no room for quantum. So I also mentioned 2 open problems. Okay, so any question?
By quantum algorithm for the Fermi-Hubbard model here?
Oh, so because I think, so first we have no hardness results for this model. So I think I would believe this problem is inside PQP. So that will be quite surprising. Not surprising, quite exciting if you can prove this is inside PQP.
All right, we have time for a couple of questions.
Okay.
Thanks for the nice talk. I know you didn't talk about how to actually find the strong guided states, but do you think there's any room for using quantum computers to actually find the strong guided states to begin with?
Use quantum computer to find the strong guided states.
Because you're focusing on if you assume that you can find strong guided states classically, then the classical cost building off of that would be efficient.
Yeah.
Do you think there's any space for thinking about finding the strong guided states to begin with a quantum computer?
So you mean like with strong guided states, you still have quantum advantage?
Yeah.
Yeah.
Maybe, like I don't know. That would be a very interesting question if you can show that.
Isn't there like an industry, like I remember Garnet Chen gave a talk at Berkeley about this. Don't they study don't they already study variational algorithms for trying to understand if you can get at least a regular guiding state?
For which one?
For just finding regular guiding states. Like I remember that Garnet Chen gave this talk once at Berkeley, which I watched online, that had this, where maybe you know the answer much better than I do, but I feel like there is an industry that tried to do it variationally, but that also doesn't seem to work so far, is my understanding.
Yeah, I think I broadly agree with the conclusions presented here. The very variational approaches that are guaranteed to work are classically exponential. So then the ones that are not exponential kind of involve a fixed model assumption that where the extent of applicability is not always clear.
Ravi?
Hi, so to be honest, I'm a little skeptical about what is why are these worst case complexity questions really the right tool to study quantum chemistry? For example, as theorists, might it be just more productive to say write down more of an average case model that looks as close to the real world as possible, but is still sort of analytically tractable, and then just sort of analyze the properties of that model? Like, why are these worst case tools? I'm just not sort of convinced that they actually say anything about reality.
I agree with you. I mean, I think I have the same conclusion as you, right? So like the ground energy estimation is quite hard in worst case, but that shouldn't be something we focus working on, at least if you want positive results. And also here, that's why I'm writing quantum algorithm for this model instead of talking about complexity results of this model.
But isn't the conclusion from the last talk that quantum advantage must be in the worst case corner?
Well, there's a distribution over that worst case corner, you know, and that's the one we want to find.
I also think like if you're looking for quantum advantage, worst case it shouldn't be something we are working on. I agree with you.
Yeah, like a worst case corner, there's still a corner there, right? There's no such thing as a worst case instance, right? But there is a corner that is classically strongly correlated or whatever. So can we find a model that is sort of sampling from that corner and then study that? That might be a better approach.
Yeah, but I think there are also a difference between like a quantum worst case and the worst case in problem in classical chemistry. I mean, I think for 95% of problems, I think it's classically easy. So in that sense, like they really want to use quantum computer to study, for example, strongly interactive system, which is hard for them. Yeah. There was a question?
Yeah, thank you for the nice talk. So about strongly guided states, at least this notion. So whether or not a strongly guided state is basis dependent, right?
Yeah, exactly. Yeah, that's a very good point. Yeah.
So I was curious if there's any like thoughts about the problem of finding a basis in which a state which is known to be a guided state, right? Like it has good overlap, but is there a task of finding a basis for which it is strongly guided?
Yeah. So for strongly guided states, I think currently there's no similar results. But for stochastic Hamiltonian, so stochastic is also a basis dependent concept,
right.
And their work on saying like finding the right basis is hard, something like that.
Yeah.
Mesh, do you have a question before? No, okay.
So to solve your Fermi-Hubbard question, I would just have to write down a good guided state, right?
If you can, that's yeah. so for this model, like the comment is, I think this is one of the example they believe is strongly interactive system, which according to the students who working on Fermi-Hubbard model, they told me they think their classical algorithm are not that close to ground states. So the overlap decays exponentially fast.
Can you say that again?
So first, disclaimer is like I'm not working on numerics. So this is based on, I asked some people who working on Fermi-Hubbard model. They say that for the hard region, they think their classical algorithm are far away from ground states. Yeah, so if you can write down a guided state, that would be.
I haven't done it so far.
Right.
Pretty good.
Let's thank.
That's a final question.
Yeah, I just want to say there may be one aspect of like realistic problem that's not captured by local Hamiltonian problem, which is realistically you care about observable expectation values. So you actually need a spectral gap in order for the ground state to be well defined. Whereas you don't need this if you only care about energy, right? So I think this question about whether it's really close to the Fermi-Hubbard model ground state is related to the gap problem, right?
If
you consider gap, the problem may be even harder.
So first, in this, I agree with you. I heard of this. They say why Fermi-Hubbard model is classically hard is because the competing phase, which the energy gap is extremely small. But in terms of this formalization, if you allow a decision gap, that shouldn't be a big problem. But I mean, I agree with you. Like study like observable value of ground state or thermal states is a more natural question than just asking ground energy.
That should be harder. Like you can, if you wanted to estimate observables on ground states, that's provably harder than QMA itself. It's p to the QMA log.
Yes.